can go helter-skelter. Like you can start with the 0, 0, 0, and then put 0, 1, 1, and then 0, 0, 1, and then 1, 0, 1, whatever. The problem is when it comes to debugging, you are going to have more difficulty in trying to figure out things. More importantly, who is going to look at your solution, such as myself, in a midterm exam or projects or whatever, I'll be scratching my head if you show something that is not working out to debug. Secondly, this is from past. The last 2 years it has settled down. People will not follow the discipline format of inputs. Then they will also have duplication. For example, a 001 may appear in two places. I'm just giving you an example. A row may be duplicated elsewhere without the person realizing about it. That means your truth table is not going to do what it is meant to do. Secondly, the output section, something that you examine each row and you decide as to what that output should be. Should it be a true or a false is a decision that you make. The decision that you make is what's going to go into the algebraic equations, and that's what is going to go into the software. And if it is incorrect, your process is not going to behave exactly the way you thought it should work. So these are all points. So out of this, you have candidates on the output, 4 ones and 4 zeros. So if you write a logic equation or a statement first, P prime is true when row 2 or row 5 or operation, or row 6, sorry, repeat, row 2 or row 6 or row 7 or row 8 is true. One of them needs to be true for P prime to be true. So this is where you will start putting the equations, and I have already explained this slide, so I'm going to go straight to how you're going to now put the equations together. We are currently looking at three basic logic operators, which are the and the or, and the not. Okay. If this has been introduced in your earlier ECE courses, this is what, oh, my pen is, highlighted. Okay, so we are looking at these three: an and, an or, and a not. That's the symbol everybody uses. Okay. The algebraic operator is shown here. Okay. And the actual meaning of the symbol set is shown here. So this is what we are going to follow. Okay. So as I said before, output has 4 ones. Can we take the 4 zeros? We'll look at it in my next example. Yes. So right now in equation form, Boolean logic expression for the console block example. This is row 2. This is row 6. This is row 7. This is row 8. So P prime is row 2 or row 6. Not to be confused, I'm going to reduce my size. Go to a pen. Okay, so this is R, not to be confused with the plus sign. Okay, this is also an R. This is also an R. So it says P prime would be true when not S and not L and P. That's row 2. So that's one combination. Or S and not L and P. Or S and L and not P prime. Okay? And not P prime. That is wrong. And not P. P prime is here, the output. The last is row 8, which is S and L and a P. This is 1, 1, 1. So these are coming straight from the truth table. If you take a programmable logic controller, you can keystroke this program into the console of the PLC. It should work. It's not a big deal in this case. It's a very compact, very simple problem. But problems can become complicated. So attempts should be made to see whether the equation that is shown, the logic equation shown, can be pressed or optimized. So there are lots of theorems, just like in ordinary algebra. Boolean logic has its own theorems. They can be used, brought in, to simplify the logic so that the truth table equation coming out of the truth table is in a more compact form. Okay? So what are those theorems? Okay. The very fundamental two theorems that form a backbone for the rest, and which is what you might be using most of the time in reductions, are shown on the slide. So what does the first equation say? An output X is true if B is on and in brackets input A is either on or off. Okay, that's the equation that has come out from some process. Okay, so A with whatever that is shown in the bracket, A or not A, will give you, well, I don't care, means it's going to be A. So if A is true or not A is true, we'll reduce it to an X equal to B. Okay, so two theorems have come into the picture here. Okay, what are those two theorems? First one is called the inclusion theorem, which says A or not A equals 1. If you see an expression such as what is shown here, you can use this theorem and say it's 1. Then comes the characteristic theorem, which says A and 1 is an A. Okay, so these two in combination will give rise to more theorems. I am not going to go through every one of them. It is not actually, it's math. Okay, and these are there for dinosaur days. They've been there for a long, long, long time. They are called the Boolean logic equations or Boolean theorems. Okay. So what I am going to show you is a list of theorems that one can apply to any process problem, not necessarily the one that we have applied it to the one that was shown, which is the console lock, but it can be applied to more complex problems. So the first set is called the characteristic theorems, which was shown on the previous slide. There are 4 of them. Then the commutative law, which is coming next. Then there is an associative law, followed by a distributive law, then an independent theorem, the negation theorem, then inclusion theorem. What I have highlighted in yellow, green, pink are most widely found in order to produce equations. Absorptive law, reflective theorem, consistency theorem, De Morgan's laws. So if you have 1, 2, 3, 4, 5 plus another 5, 10 theorems in front of you, you should make attempt to use whichever theorem would apply to make the equation, if possible, reduced or optimized or compact. Because PLC, unlike your desktop or a laptop, are not going to come with 500 gigabyte or 1 terabyte of memory. They are small unit and they are also sold for a much lesser price as a result. Plus, they are very dedicated to process control. So, the shorter or the compact your code, better it is for running it more efficiently. Another consideration, remember I told you once, the lines in the PLC code are scanned from top to bottom at certain clock speed. That clock speed is increasing now. When I started my first introduction to PLC, started using, I still have one of them not working. It's an Omron PLC, I would say 1986, 87 era. The clock speed is the same as your power supply on the wall, which is 60 hertz in North America, 50 hertz in Europe. So, 50 hertz per second was high speed, not anymore. So, if it was 50 or 60 hertz for those older PLCs, very long programs as it scans from top to bottom has some issues. The issues are, yes, it will scan. It is likely when it starts scanning the first line, and this, let's say you have 1,000 lines in your code, and then 894th line, conditions were right, and the output became true. But PLC is starting to scan from the top. By the time it hits the 894th line, who knows, the condition might have changed and the output might have turned off, which is not good for process control. So if the speed, that's the reason why you can't make the programs compact. The second reason is if the clock speed starts increasing, you will scan 1,000, 10,000, whatever, much faster, right? So the PLC these days are not on 50 or 60 hertz. They are in gigahertz speed, much faster because of the clock speed. So will it hurt? Well, I'll give you an example. I want to control a nuclear power station with a PLC, where I am monitoring several parameters such as pressure, temperature, flow rate, whatever. And I have a very slow PLC. Let's assume. As I'm scanning, well, the core temperature went up a very dangerous level. What my PLC is taking its time in scanning through the whole plant a process for that nuclear reactor. Well, by the time it goes there, maybe the meltdown has already started because of slow speed or because of very long, non-compact program. So it is important that you try and make the program as compact as possible by using these theorems to see whether any further reduction can be made. So look at the console log example. We had this equation. E prime is row 2, row 6, row 7, or row 8. R. Now, take the first two. What's the common? Not L and a P, correct? So, not L and a P. Take this out, right here. And what's inside is not S or S. What will happen to it? It'll drop down to a 1. Drop down to a L not P. Take this row 7 and 8, which are this. Okay, SL is the common factor. Side it's P not or P. This reduces to 1 as is shown here, and the whole equation now is a bit more compact than what you started with. Okay, so the actual meaning you can check to see whether this equation makes sense, because if, as I said before, if your truth table is not correct, you may not land up with this equation, you may land up with another equation. So you should check by looking at it to see whether it makes sense. Okay, so what is the right hand side telling you? Key is absent and the process is running. That's the first term. Key is absent and the process is running. That means operator came, switched on the process, got the process going by pushing the on off switch S to a on position, right, and walked away. So if somebody monkeys around with that on off switch, they can't do anything else. The key is not there. They can't unlock the console. They can only monkey around with the power switch. Your process should not be shut down. That's the first term that is making sure process is foolproof. But there is another term, SL. Switch is on, it's on the on position, and key is present and not removed yet. When would this happen? When the operator wants to start the process before he takes the key out, what will he do? Well, he will switch on the process and take the key by locking it out of the console. So the second term takes care of the startup process. The first two terms take care of the process of running after it was started. If one of these conditions fails, boom, prime will die. So in this case, distributive law, inclusion theorem, and characteristic theorem, three theorems have been brought in, make it a bit more compact. Now, every console in CNC machine and robotics or whatever sensitive processes have a console with this type of arrangement. Now, you have three inputs here. It can be a lot more. Okay? For example, in my robot console, on the surface or on the console, there are about 16 or 17 switches. But inside, there are many more. There are close to about 484 inputs and outputs combination that are primarily triggering alarms. If one of the motor is down, well, it'll come up on the panel. So there are a lot more inside where these equations are not going to be as simple as what I have shown. Now, you may ask, is this the only route? I would say not necessary. If I'm into an industry where my job is not to make the what's inside the uh, cabinet, but I got a subcontract to make the door of steel, aluminum, or whatever, drill holes for the switches, put the, in this case, put the console on off switch or the process on off switch, and put the key lock by getting a key and a lock from some other whatever, and then make it work for the people to whom I'm supplying this door or assembling the rest. If that's my bread and butter, I'm making 1,000, 10,000, 15,000, who knows, per year. Would I lock up a PLC, which by itself in this case would cost you 250 plus? Not going to make any money, or the other person is not going to make money, or you're going to pay a lot more money. One of them. So if it is a fixed automation, I can go through another route. What is the another route? Okay. So you know the AND, the OR, the NOT operations. They are available as analog chips. You can buy them in bulk for 10 cents, 20 cents. So in this case, I can do this. I can do this. An AND, two inputs, an OR, two inputs. NOT is represented like this. Puts bulk, buy in bulk, 50 cents. Then I wire it up. So if I look at the equation, not L and a P. So what I have to do, I translate this. Should have put another duplicate slide. That's L as an input. Okay. So the output will be not L. And I take a P and put through an and the output will be this. Let's call as second part. I have an S and an L. So I take another AND, S and an L, output comes here. So this is output 2. Okay, so I join these two. No, sorry, I don't join them. So I take an R output. Now R, take this. So this is a R operation. So this joining the line. Can erase it, but find the eraser and move. So this line is not there. There are two independent outputs going into the R as an input. The output from the R circuit, which is the final, will be P prime. So $1, let's assume, for wires and chips and whatever. Let's assume a little printed circuit, whatever, mass produced, maybe $2-3. Then you hire somebody to put this together, solder, whatever. Pay another $10. So totally under 20 bucks. You might be able to get a little circuit board with all the components populated. And once you do one, go to your printed circuit production. Don't need to have somebody solder all the wires and so on. Surface mount process will do it all for even much cheaper price. But the problem is this, whatever circuit that I have put together using hardware logic devices is only good to this process control involving console lock. If something changes or if I want to add more, I have to throw whatever I bought or whatever I made because it's not good anymore. Or because I can cut them, that's not productive operation. So hardware can also be done if it is a fixed automation and has got nothing else to do. But you can imagine if these equations become complicated, this goes to more complexity. You have got to do more things. Where a PLC would give you more flexibility. Okay, if the process changes, I'm going to add a few more. Or I'm going to move my controller to controlling a different process altogether. Easy. Just take the PLC and rework your program, download, and you're done. Okay, so keep that in mind that's how we can move. I will show this diagram. Comes up in another slide, I think. I'm not sure. Yeah, later on. Okay. Any questions? Well, now I hope everybody is around. The midterm test. Now that I have got the which is E2327. As I said, I will send the email. Time is 6:30 to 7:30, October 20th, which is a Wednesday. It's 50 minutes to 1 hour long, but it's worth 10%. You are going to study only the CNC section, not the PLC that I'm doing. So, about 75 slides, I think. Here, plus slides, as you all figured out by now, is not complete. I've been talking over the slides quite a bit. So, if you have attended the lectures, if you have gone through the notes, there should be no surprises. It will come from the material you have read and the material taken notes or whatever. That's the advantage of closed book. Open book, I cannot ask anything from the notes. So I got to, which what happened last year. Made it difficult. So I can't just say, yeah, you have all the stuff in front of you, you can do whatever. I'm going to ask only from what you have. So there is no trick that I will pull. I'm only examining your understanding of material I have presented. Okay. Any questions? Not have to bring your own answer sheets or so on, whatever. I will supply 10.5 by 11 white sheets. Obviously your pen. And stapler will be staple the sheets. It's exactly 1 hour long. Unless you want to finish and go away early, which one person or two did stuff. Okay. Any questions about the midterm? No. Have I said it? The answer is no. This weekend, because I got the notification yesterday, it's to go through COVID committee. Who knows? Okay, so you saw one case study involving a very simple process draw. Now I'm going to go to another case study, which is going to extend the complexity of the previous example. So, what is the problem? I am sure during your summer work term or summer job or industrial tour, but I've seen punch presses, which are very widely used in industries. From bending small cabinets to bending larger sheets, thicker sheets. Okay. So, preforming a part to go into something else. Example, if you take your car, wood, not machined. Bumpers, says they're all plastic. They're not machined. They are injection molded. Your doors, if they are made of metal, not machined, pressed on heavy duty presses. Okay. So the punch press may look something like this, but this is a very small scale, but it shows the operation. You have a die which is machined exactly to the shape that you want the part to be pressed. So you first make the die out of a CNC machine, small, large, whatever. In this case, it's a very small one. So the die is held by a pilot pin, which can be removed to change the die. Then you have a punch head with the spring under tension, says stripping spring, and a guide through which a slide will go down to punch on the part. You can take the case of a stapler. I used to staple pages. Basically, it does the same thing, but it folds to staples together, hold the paper tight. Now here, it won't be like a stapler. It just presses on the die and forms the part. So replace. How is the spring going to release the force to pound on? Well, stapler uses press. Now hydraulic press, you will have massive cylinder which is powered down by hydraulic force, generating 1 ton, 2 tons, 5 tons, 10 tons, whatever of force on the die. So let's assume I want to automate this process. In the traditional way, this is how it is done. There's a die on a big machine which is already made and mounted onto the press. Operator is there in front of the machine. Machine could be 10 feet high, 20 feet high, depending on how powerful it is. So the operator manually loads a sheet, blank sheet, could be steel, aluminum, brass, whatever, and of different thickness. And then he adjusts the pressure. If he's mass producing, the pressure will stay adjusted to the desired force that it has to generate. He throws the sheet, then moves away and presses on pedal. The ram or the piston comes down, pressing on the part. Some machines, if he releases his foot, piston goes up. In some, it'll automatically go up. So his pressing on the switch is only a trigger, right? Now, this is a dangerous operation. What happens if you accidentally press the switch with your hand inside when you're loading? Well, so let's look at to see how I can automate this process using a bunch of sensors, bunch of outputs, and using a PLC uh, to control the process. Okay. So what should I identify? Like before, decide what are the inputs and outputs that you want to use on this process. Okay, so the example I am going to use for the die works like this. When the hydraulic force sent to the piston, it comes down to press on the part and then automatically returns home when it has fully pressed the part. I am going to locate two sensors. One to tell me when the piston is home and when the piston is advanced. So let's assume it is a limit switch or a photo sensor or a magnetic sensor. It could be all kinds. So I'm going to mark them as input. They are inputs to the PLC, indicating whether the machine is home or not home. Okay. So check my definition is correct. Okay, so I have put capital letter L, the small letter T, and a subscript 1 because I have two switches, home and advanced, and I'm going to call LT subscript 1 when it is home, as is here, and LT2 is advanced. Okay. So on this diagram, it shows pen. Okay, so home, advanced. This is your die. Let's assume put a plate on top, press. Obviously, form a cup. Then on the figure, S1, S2, S3, three more have started appearing. What are they? Okay. They are assumed photo sensors and forming a light curtain around the machine. This is a safety switch. If you cut or interrupt those beams, it's in a panic. Somebody is intruding. Machine is operating. Dangerous. So I have put three switches, S subscript 1, S subscript 2, S subscript 3. It can be 10 switches, S1, S2, S3, S4, S5, S10. Just for simplicity, I have taken 3. So what else? What else do you need? These are inputs. I need trigger. Okay. So this is how the piston is going to work. Press or the piston sustains the power to the punch, which is the one that's coming down during downward stroke. So prior condition would be LT subscript 1 must be true before this process has started. That means your actuator in operation. Then LT2 which is the advanced position. And once that's triggered, the controller knows, well, the press has sustained the full power and has gone all the way down and the part has been stamped. Completion of the process. Okay. So press sustains the power. How are you going to do it? Okay. That has to be an output from the controller. Turning on a pump or turning on a hydraulic valve to send the fluid pressure to the piston. That's how it's going to work. Okay. My second sentence on the slide I've already covered, so I don't need to. So, slide shows what's going to be involved in this. Not too complicated, and I'm going to show you how I can complicate this problem immensely in the real world, or how it will get complicated. I need a start button, which could be a simple foot switch. When I press it, it's true, and when I release, these days when you go to, seen it in PV Mart. I don't know how many of you go to PV Mart, repair shop, one close to my house. They have a little bucket, using as disinfectant, and I guess there is some kind of pressurized chamber, air filled or whatever, and then you have a foot switch. Press it, squirt some amount of disinfectant in your hand, and then take your foot off. It stops. Right? So that's an example of just a foot switch. So start button, which is a foot switch, equal to 1 when pressed, equal to 0 when released. Don't get confused with the piston. I'm coming down. This is start button. What would it be? It would be an input to the controller for telling the system go. And the stop button, or strictly speaking, the emergency panic curtains that are around, which are marked as S subscript I, S1, S2, S3, which I explained before, equal to 1 when interrupted. I put pressed, but when interrupted, when it is true, 0 when released. Limit switch, up and down, L subscript 1, L subscript 2, deflected, not deflected. Now you can make the different assumption and say, oh, I don't like G equal to 1 when pressed. I'm going to make G equal to 0 when pressed. The other one will be G equal. If you do that, the logic will change. Right? You can get sensors to do the other way. But if you don't tell somebody else, this is how I've assumed. If they implement the logic, as you said, it works, without revealing this is what I did, just will screw up the whole thing. Right? So, assumptions, what is stated here is must be followed by whoever is going to read. So, best is to state whatever you're assuming on a piece of paper, and I have stated. I'm not saying a start button should always be equal to 1 when pressed. Makes sense. It is on or off. That's what it is. Okay, so these are my basic inputs. Then output, ram actuation. Ram is the piston, and I marked it as A star. Why? Should soon see it. So how many inputs are there now? 1 plus 3, 4 plus 2, 6 inputs so far. How many outputs? Ram actuation. which is the A prime star whatever, one output. Now I am going to use this as a feedback. 6 plus 1, 7. 7 inputs and 1 output. How many inputs were there in this console log? 3. 2 power 3, 8 rows. Now you're going to have 2 power 7. Okay, that means your truth table start with 1, 5, 6 zeros, build all the way 1, 1, 1, 1, 1, 1. This is the last row, this is the first. Put several in between the various combinations. So 2 power 3 is 8, power 4 is 16, 2 power 5 is 32, 2 power 6 is 64, 2 power 7 is 120. You are going to have 128 rows. That means eliminate these two. You will have 126 rows in between. It's the input section of the truth table, and you, as the designer, should design what should that A prime be for all these various combinations. Now you see how it's now getting a little nastier. But if you had all the time in the world and a piece of paper and a garbage bin next to you, all kinds of assumptions which when you re-examine, no, this is not correct, throw it out. Okay? So is there a AI package that people are nowadays very happily using for everything? AI is there isn't AI, it's actually human giving rule-based system. I would put more machine learning as what you have given it. Would say system learns by itself.
Hey, Dr. Bala, you're cutting out a bit.
Yes, it learns by itself by way of several rules that you construct. Hear me? Now? How about now?
Yeah, now you're good.
Good. Okay, I think it's the internet that goes out of whack because today I've replaced my computer and I have replaced my headphone, which is a wireless corded. So if the audio cuts out, sure whether Shaw's internet sometimes goes out of whack. As long as it's recovered, it's fine. Okay, so I was talking about 7 rows. Is there a very smart, not 7 rows, 128 rows? Is there some kind of a software that will tell me, okay, tell me what are your inputs? I will analyze and tell you where the outputs are going to be 1 or a 0. Such stuff. It's not there. Every process is going to behave in a certain way that it's supposed to. Are there millions of possibilities that some software is going to analyze? No. So you, the designer, will do it. Okay, so are we going to go through 7 zeros with all the possible combination between? What do you think? So I'm going to show you how we can possibly proceed with this problem. So this table, the slide already tells you whatever I have covered. Solution simplify the problem by dividing it into 3 smaller problems. The output from the first problem feeds into the second problem as an input. Output from the second stage goes into the third stage as an input. And as we modularize the number of inputs that we considered in the first one, if it is 4, 5, will reduce to a 1. Right? So you're going to segment the problem. And I will show you in this example how you're going to do it. The first thing to do is look at those panic switches, S1, S2, S3. What are they? They are actually 3 switches. Are they independent? Yes, they have to be independent switches. They are not wired in series. They are wired in parallel for this operation. You trip one of them, boom, I want an output, which a parallel circuit will do. Okay? But not to be confused of wiring switches in series or parallel. Just for now, assume each one is producing its own output. The sensor output is an input to the PLC. Okay, so as far as we are concerned, we are not going to treat the S1 and S2 and S3 as an output. We are going to treat this as an input to the PLC. So put the truth table. Like before, the console lock example. Okay. Now, this is the discipline that I'm talking about. Take the first 4 rows, totally 8 rows. You start with the 0, 0. So 1, 1, 0, 1, 1. That represents this. Then add a 0, 0. Then this flips to a 1, and this whole thing repeats. Oh, 1, 1. That's what you see in the truth table. What happens if it is a one more row added? So you're going to add a 0, 0, a 0, a 0. Okay. Then flip this 0, 1, 1, 0, 1, 1. These two will be zeros. Then the next stage is this still stays as a 0, 0. This flips as a 1, 1, 1, 1, and this repeats. So the last row or last 2 row columns will repeat segment by segment. As you see here, this is a repeat. So it'll become more bigger, but I'm now going to show you how we can deal with this problem. So can you imagine putting a truth table with power 7, which is 128 rows, which is 7 zeros all the way going to 1, 1, 1. I can't even fill it up here. So I, as the designer, decided S1, 0. That means no output from it. Nobody is interrupting the beam. And S2 is 0. Nobody is triggering that second switch. And S3 is 0. Nobody is triggering that switch. There should be no alarm coming out of this combination of switches. So S is 0. It's very easy to note here. If any one of these switches is 1, boom, output should be 1. Okay. No other combinations are going to be arising out of this 3 input, 1 output section. Okay. So what should be the logic equation? S is true. S is an output that signifies the state of S1, S2, S3. S is true if row 2 or row 3 or row 4 or row 5 or row 6 or row 7 or row 8 is true. Pretty long equation. Can I do this? S is not true If S1 is not true, or S2 is not true, or S2 or S3 is not true, I am considering only the first row. By logic, they both mean the same thing. Either I go here or go here, which is making more sense. Go to the first row and simplify the equation. S is not true. Write one line equation to represent this truth table. Done. Makes no sense to go to the other route, right? So that's the only one that's going to be controlling the process from truth table, not S. It's true. When I put the sign equal to, it means yes, it's the output is coming. S is not true when S1 is not true or S2 is not true. Am I making a mistake? Can somebody correct me? S is not true if S1 is it AND or an OR? It's an AND. S1, not S1, not S2, not S3 is true. That's the equation representing 1. That's coming straight from the truth table. Take this, you can keep it as it is, or you can represent it in different ways. Using De Morgan's law, not S, is S1, S2, S3 with one NOT operation going all the way. So this is now an OR, which is easier to implement this. In this case, it is not that complicated, but this is more compact. I can also go this way. Okay? So there are many possibilities. Bottom line, the logic, S is true if either S1 or S2 or S3 is true, which is this equation. Right? So what did we achieve out of this? We combined 3 inputs into one output. The 3 inputs that we are considering is S1, S2, S3. To give rise to an intermediate output S to represent variable that is going to now come out as a single variable, go to the next stage as an input. So the output from this analysis is input in the next stage, right? Now, is this problem as simple as what I am presenting in the take a real punch press? Yes, there is an hydraulic pump that is going to put hydraulic pressure down, and they are 40,000 psi. They are built solid, but there are hydraulic lines which can leak. You want to put a leak detection sensor by monitoring the pressure. You want to make sure if it is 30,000 psi are supposed to be, you want to make sure it is plus or minus a few psi. If it drops to 10,000 because of some leak, you're not going to have a quality pressing. Probably useless and to be thrown out as garbage, wasting material. So you will put more sensors to detect to measure the actual pressure. What else? Well, I want to adjust that pressure. So I want to I want to press different types of materials, right? So I want to adjust the pressure for aluminum. I want to adjust the pressure for steel. I want to adjust for something else. So I want to know what is the type of material that is loaded onto the table. So I can put a material sensor, which is going to tell me whether it's aluminum or a steel or whatever, and adjust the pressure automatically. And in our study, we did not consider anything about part actually being present on the table in the right alignment. An operator throws, he or she may lock it up against the picture. If the robot or something else, that's what will happen, is used to put the sheet in. It has to do so provided there is no sheet on the table, provided there is sheet available for it to load, and provided it gets a command, okay, go load. And it also has to get a different program to take the part, stamped part out and throw it into a different section. So you are going to expand in terms of number of inputs and outputs to much larger input output problem where the 2 power 7 will become 2 power 11 or 2 power 12, who knows, because you are going to involve more and more sensors. So in the real world, it is quite complex, will become complex. And when I say is complex, yes, it is solvable by looking at more smarter way of segmenting the problem. I'll give you one example. You all know Magellan, which is Bristol Aerospace, was Bristol Aerospace. You know that there is a Rockwood plant, which is under Bristol or Magellan, not exactly inside the city, very close to Headingley, near the penitentiary. You won't see it because it's a hidden section far away from the highway. What is the what do? They make what they are making now. They're still around. Black brand rocket motors, shells. Then they fill it up with its solid propellant and put all the electronics, then ship it out. It's used for launching satellites right out of Winnipeg. Okay? So they are called black band rocket motors. I was asked to help them 25 years ago, 20 years ago. They had a process where after you put the solid propellant into the shell, before mounting all the electronics and closing the shell, solid propellant, if you have dealt with the expandable foam, doesn't form a nice and clean flat surface. It's all over the map. So you gotta make the surface more or less planar before you mount the next stage. How would you do it? You grind propellant and grinding. What a good combination. So this process was done using a custom developed robot by a company in Ottawa who supplied. The whole stuff is not electric, is fiber optics, buried in a pit into the ground with a concrete wheel around it. Then it will be closed whenever it's in operation with slabs made of steel, so that in the event there is an explosion, it's contained. So I was asked to help because the robot wasn't working right. So I went. Obviously, it was supplied by some consultant who made a kill. Not about 25 years ago, but 20 years ago. If you take one of the larger lecture rooms in engineering lecture in the EITC building, such as the one that you're going to write the term exam, capacity of 130 people or whatever, and look at the wall. Somebody had who would design the logic, the consultants, When I pulled out the logic, it would almost fill that wall. Too complex, very unwieldy, very difficult to debug. So I told Bristol, okay, give me a project. I will have a graduate student to help me write the software and make it work. It took us about 4 months. The graduate student was paid. I did not take any payment. Project was done, and it's much more compact, easy to debug, very well documented. So this is an example where don't pay attention to compactness of the logic. You can go whatever way you want and make it big. Okay, so but after this project was finished, yes, he was a manufacturing engineer. He was a graduate from University of Manitoba, but didn't take any of my undergraduate courses because I was not there. Came to me that he wants to do a master's part-time with me, and they have several automation problems. Master's MEng, as it's called, doesn't require a thesis. You have to do an extensive project. So together we did an automation of coating the Black Brand rocket motor with an insulation material before applying the solid propellant, which is highly carcinogenic. It also has to be applied in several stages by curing in a chamber whose humidity is close to 90% and the temperature is also close to 100 degrees Fahrenheit. And you can't stay in the chamber. You're fully dressed with all protective gear for more than 15 minutes. So it was done in several stages. So he said, can this be automated? Good, that's your problem. Let's sit down, chalk it out. It took about 2 years to automate this. About $12,000 of investment, assuming that the student or the engineer who worked with me was fully paid during this process. Bristol supported it. They had 13 rocket motors for contract to be delivered. The money of 10,000 was literally got back. 2 rocket motors. So payback period is very fast, very reliable, very accurate, no human involved. It's a completely process control automation using a 2-degree freedom machine that will go in and do the process of coding. So that's another example. It's my mind. Okay. Now, the next stage is go to next stage, which is stage 2. Create another truth table. What are the inputs and outputs? I want to introduce a new variable. Monitor whether the machine is running or not running. How will I in the real world monitor this? I can put a pressure transducer at the extension chamber of the piston. If it is not extending, there is no pressure, 0. And put another transducer on the inlet section. Use the 2 of them to monitor whether the piston is coming down, that the process is running. So the variable is R, which was not in equal to 0 if it's off. Okay? And to an output R prime, like the way we did in the first stage, to represent the output as opposed to R, which is an input coming into the system, because they're going to write the logic equation. What else? These are my inputs. G is the starting of the process. S is the panic that we did in the previous case. R is the process running or not running. What's new in this? The S is old from the previous stage. The G is new. And the R is new. So we have three inputs and one output R prime. Again, a 8-row truth table involving. Look at this. This said constructed the truth table. No different from the previous section. But this is different. I, as the designer, decided for the possible combination R prime will be true in row 2, row 5, and row 6. Nothing else. So in this case, we have 3 ones and 5 zeros, which is going to be more compact. Writing an equation for the 3 ones versus the 5 zeros is going to be. So alarm says shut down for the lecture. So is it making sense? I suppose so. So there is a lab this afternoon. I will be sending an invite to, I'm sure I have to check, belong to the Tuesday group. That part cut. Tuesday group as usual. So, any questions? Anybody? The lecture is over. No? Sometimes I worry when there is a silence whether my audio is going, not going. So everybody heard?
Yeah, we can hear you. It makes sense.
Yeah. Okay. So, see you guys this afternoon. Those who are in Thursday group. See the rest on Tuesday.
Thank you.